The heavy lifting. Now we can put it together with the data that I promised you I would explain where we got and understand the history of the universe in the past and into the future, because I said that understanding these parameters determines everything. Now, let's see how that goes, and we'll talk along the way. Early days of the universe. Remember, early days of the universe would have been radiation dominated. I talked about the fact that into the past, matter density increases like 1 over a cubed as a gets small. Radiation density increases like 1 over a to the fourth. I didn't say anything about dark energy density because, remember, that's a cosmological constant. That completely does not change. The energy, the density of dark energy does not change with the scale factor of the universe. And so this tells us in particular that if it's 74% of the energy density in the universe now, in the past, when A was smaller and radiation and dust were denser, it was less important. So early in the universe, the cosmological term plays absolutely no role. And remember that the universe is radiation dominated until about 55,000 years of age. And what does it tell me that it's radiation dominated? Radiation dominated basically tells me that rho radiation behaves with the scale factor like a to the minus 4. And so I plug that into the Friedmann equations, and I find that the scale factor, as I promised, increases like the square root of time. So the universe starts expanding very rapidly and then slows down. Of course, this region over here, where the universe is very tiny, is not the first, just the beginning of this graph is something we'll focus on a little bit later. But for the first 55,000 years of its universe, this is the plot of the scale factor as a function of time. I can sew this on to a graph that describes the current universe. Of course, here the scale is billions of years, so I've completely ignored the little tiny bit here that includes the beginning of the other graph. And so I've imagined starting at 0 with a matter-dominated universe. Matter domination gives me the behavior I described. The scale factor increases like t to the power 2/3. And there's a transition from matter domination to domination by dark energy, which, remember, today there's about 3 times as much dark energy as there is dust. Remember, I talked matter, dust, same difference. The transition occurs in the past when the density of dust was about 3 times what it is now. The density of dark energy not having changed, they would have been equal. And prior to that, dust would have been denser. That happened at a redshift of about 0.4, or at an age of the universe of about 0.6, what it is now, or about 8 billion years. And we see that over here. And this heralds a transition from early times when the scale factor behaved like t to the 2/3, a power smaller than 1, so that the expansion was decelerating, to the behavior at large times. At large times, as the scale factor gets larger, radiation has already been diluted to insignificance. Dust also gets diluted to insignificance, and what is left at large values of A, if the universe ever gets large, and there is a cosmological constant, it will eventually take over. The expansion driven by a cosmological constant is an expansion where the right-hand side of the Friedmann equation does not depend on A, does not change with time at all. This gives us the closest thing to a constant expansion. It's not a constant expansion in terms of the rate of change of A. It's a constant expansion in terms of the Hubble constant is in this case constant. That means, remember, the rate of change of A has to accelerate. In fact, it corresponds to an exponential growth of the scale factor. And you can see that at late times, as this term takes over, the curve turns over to an exponential rate. And because we have a non-zero cosmological constant or dark energy component, we predict that in late times we'll have exponential expansion of the universe. We live right about here at 13.8 billion years, where the scale factor, by convention, is exactly 1. Notice we are not far from this turnover, from the transition from dust-dominated to cosmological dark energy-dominated universe. We're at the region where expansion, which had been slowing down, is already accelerating. this is the exact form of the function I plotted, but more important is that it's exponential at one end and t to the 2/3 at the other end. And then remember, way down here is a little region where it behaves like t to the 1/2. That, if you want, is the history of the universe. Note that understanding the current cosmological parameters, once we figure out how we measure them, we can post-dict the entire past of the universe and predict its future, and we'll see what all that means. As a first application of all of this, let's introduce this important issue, not unrelated to Olber's paradox, of particle horizons. So how far can we see? In flat space, normal space, you can see all of the universe, but you just see farther and farther. But if you want to see things that are farther from you, you might need to look farther and farther in the past. But our universe, as Poe reminds us, has a finite age. So the question is, can we see the entire universe? What fraction of the universe can we see? And that fraction of the universe that we can see is called our particle horizon. And it turns out that if you take any observer, of course all observers are the same, take some co-moving observer, sit him at one point throughout the history of the universe, and ask what fraction of the universe he can see. Well, the universe is infinite. We're going to talk here about a flat universe. Remember, I have a strong bias to a flat universe. And I want to ask, which other observers has he seen? Okay? And a good way to describe this is what we'd call the size of the observable universe. This is the distance from us to the most distant objects we have seen, or can in principle see. These are the objects that we see so long ago, so far, that the light left them at the time of the Big Bang. So another way to ask the question is, at any given time, what are the things that you see as they were at the time of the Big Bang? And so objects on the particle horizon are the things you see at the time of the Big Bang. Now, of course, in the radiation era, for example, you solve the equations and you see that the distance to the particle horizon increases with time. In fact, it increases linearly as twice ct. So if you are looking at the universe a second after the Big Bang, you can see 2 light seconds in each direction. Note, 2 light seconds, despite the fact that light is moving at the speed of light. How is this happening? Well, remember, this is the distance now, coordinate distance, at time 1 second, to those observers whose light you are seeing at time 1 second, from which light took 1 second to reach you. But of course, in that 1 second, those observers themselves moved, so they are now 2 light seconds from you, because expansion has carried them that far. In the matter era, solving the same equations, you find that the objects you see, again, ignoring the little bit of expansion during the small radiation era, in a matter dust-dominated universe, the distance that you can see all the way back to the Big Bang at time t increases with time as 3ct. You plug in that complicated function that describes the transition region between dust-dominated and dark energy-dominated, and figure out how far we can see today. And again, this is not how far the light has actually traveled. That's an ill-defined question. This is how far today are the objects in today's coordinates, are the objects which we see as they were back at the Big Bang, and if we could see them, they would be 46 billion light years away. Note, this is a lot more than 13.8 billion light years. Light has traveled for 13.8 billion years, but the objects that it left 13.8 billion years ago are now a distance 46 billion light years away from us, so we can see, in principle, a big sphere around us whose radius today is 46 billion light years, and that sphere is still growing, but that growth stops in the sense that when you move to an asymptotic expansion, then at large times, when we're describing an asymptotic expansion, the distance of the horizon becomes just a constant number, some constant distance, times the scale factor. So basically, you're seeing the same objects. You no longer see, and once you hit exponential expansion, more and more of the universe. The ultimate limit, the things that we will see out to the end of time, the most distant things we will ever see, are those which are currently 62 billion light years away from us, and anything that is currently farther than 62 billion light years, we will never see, because the expansion of the universe carries them so far farther away from us so fast that light from them will never reach us. So if you want, this is the size of the universe we have observed so far. If we had observed the universe, I don't know, 6 billion years ago, and you imagine that it was dust dominated, we would have seen about half that distance, because in the dust dominated world, the horizon distance grows linearly with time, and the growth is slowing down now. When I say half that distance, I mean we would have seen half that an eighth as many galaxies were visible 6 billion years ago as are visible now, assuming that galaxy density has not changed, which is probably false. And there's an ultimate limit to how much we will see. As I said when I discussed Olbers, it's not just that we have not yet seen everything, but even if we wait till the end of time, we will only see a finite extent of the universe, only some finite chunk of universe. That chunk will grow, but we will only see a sort of finite list of observers asymptotically. You can ask a different question. That defines a particle horizon, and here is drawn, our particle horizon is drawn in this dashed line as a function of time, and you see that indeed, that's this dashed line over here is our particle horizon, at times from the beginning of the universe to 25 billion years, so right over here, the horizontal line is where we are now, and these are at any given time, all of the things, all of the parts, all of the galaxies, if you want, co-moving observers are at rest in this frame. They move along vertical lines. So the horizontal distance measures distance in today's coordinate, in today's universe. And so you see that we will see objects by 25 billion years into the age of the universe. We will have seen out a little bit past 50 billion light years, and eventually this asymptotically ends at about, I said, 62 billion light years. And by today, we've seen out to about 46 billion light years, despite the fact that the universe is only 13.8 billion years old. And that's one question you can ask. The other question you can ask is, take today's universe. So think of this as a space-time diagram. Here is the universe of today. And say, suppose that something happens, which of the events that are happening in today's universe will I ever see? And that answer turns out to be a different question. That defines something called our event horizon. So you can draw, and this is the picture of our event horizon. It separates, and that, it turns out, narrows with time. In other words, these are, of course, these are all of the events inside this, which at any point in the history of our little corner of the universe will be visible. So if you want, this is the analog of our past light cone. At any given time, this is our light cone now, and if you add up all of the light cones into the infinite future, you get this event horizon. So something that occurs today here, of course we can't see it, but if you give light time, will eventually if something that occurs, say, here today, of course we can't see it, but eventually someone on Earth will be able to see it. Something that occurs farther than about, what is it? About 15, 16 billion light years away from Earth. Today will never be seen. We can see the things that are 16 billion light years as they were in the past, but we cannot see anything that happens 16 billion light years away. Today, we will never, ever, ever see. And in fact, because of the exponential growth past once the cosmological term takes over, you see that our event horizon shrinks rather rapidly, and into the future, eventually, if you ask what are the objects that we will be able to see as they are 10 billion years from now, which is about here, you see that they form a small fraction of the object who's from today, which we will see. And so over time, we get to see less and less of the universe. In that sense, we get to see more and more of its past. But if you ask, say, stars started forming at some period, over time, we see less and less of the current history of the universe. An object, and what you see is that over time, a given object that is stationary, say something 20 billion light years from us, Well, we could have seen what happened to it at the Big Bang. We could have seen what happened to it at the age of 5 billion years, but by about 10 billion years, we lost it. Anything that happened to this object later than this point will never be seen at Earth. So over time, objects are leaving our event horizon. So what does that mean? Of course, they won't. It's like an event horizon of a black hole. It's not that they hit the event horizon and poof, disappear. What happens is that the light from this object experiences an infinite cosmological redshift as it approaches the event horizon, because essentially the time for light to get here becomes infinite. We get an infinite cosmological redshift, and so we will see objects dimming as they approach. So as the light from this object starts to reach us from bits of its history, as it approaches the event horizon, we'll see it more and more redshifted, and it'll basically dim itself out of existence, and of course we'll never see it cross the event horizon. So we have our particle horizon, which is all of the bits of the universe that we can see since the Big Bang. Let me clear the picture up a little bit. So we have our particle horizon, which currently, at the present time, involves all the parts of the universe that we can see as they were at the Big Bang. This is our current particle horizon, right? It touches here. This is our current particle horizon. This is what we see, as we see all of this part of the universe at some time after the Big Bang, whereas in blue over here, this is our current event horizon. These are all the objects today that we will still one day see. So in some sense, with time we see more and more of the ancient universe and less of the current.